Hi all, we're back with the video on EPOC. So, I just want to go through the general theory in this video. So first of all, let's have a look at what EPOC actually means, okay? So, let's take each word individually. We've got excess. Excess means more than I need, okay? So I've got an excess amount of oxygen that I am consuming. Okay, I'm consuming it, I am using it. Okay, I've got excess, I have got more than I need. And then when is this taking place? It's taking place after exercise, okay, post-exercise. So I'm using an excess amount of oxygen, okay, after exercise. Okay, now this happens in two instances. Okay, I want to look at the first one, which is going to be the fast component. This is known as the lactic component. So, I'm exercising, alright? I'm working at quite a high intensity and I am going to use my ATP PC system. Okay, remember the ATP PC system is where creatine kinase detects high levels of ADP in the muscle because I've broken down my ATP and I need to resynthesize it rather quickly. So, I have a phosphate and I have creatine and they are stuck together as a bond and then they are broken apart. Okay, when I break them apart, it releases some energy so that I can resynthesize ATP. Now, at the end of exercise, my phosphates and my creatine have all been ripped apart. Okay, so I have P's and I have C's just floating around in the muscle. Now, if I don't have that, I can't work at a high intensity. Therefore, in this time, all it is concerned with is resynthesizing my stores of phosphocreatine. Okay? Because if I don't have my phosphocreatine stores, I cannot use phosphocreatine as an energy source in the ATP-PC system. Okay, so let's kind of have a look at how that works. So, when we're looking at it, we've got this graph here. I'm looking at oxygen consumption there. Okay, now you've seen a similar graph to this before because I have my steady state up here. Okay, this is my oxygen consumption. We've looked at it as minute ventilation. So I have enough oxygen here to resynthesize aerobically. However, at rest, if you remember the start of the graph, it looked like this, it was this low. Okay, let's say here, where it is flat, that is 20 litres per minute. Okay, so it was 20 litres per minute here and it's 20 litres per minute here. Now, the amount of oxygen that I am consuming is based upon the intensity of the exercise. So right now, me sat here, you watching this, we would be at that 20 litres of oxygen per minute. Now, here clearly it's a lot higher. Right, because I need more oxygen being transported to the working muscles. But then as soon as I finish exercise, let's say I sit down, okay, all of a sudden, as soon as you sit down, you are working at the exact same intensity that we are right now. However, what you notice is when you're sat there, you would be breathing a lot heavier. Yeah, your tidal volume would increase, your breathing rate would be elevated for this period of time. Okay, and then eventually it would start to decrease. But this is EPOC because I am using an excess amount of oxygen for this time. Okay, I'm using more than I need for the intensity that I am working at. So, it says here time in minutes. Well, we need to look at how long is this actually lasting for? Well, between here and here, will take about 2 to 4 minutes. Okay, here would obviously be 0, but for EPOC, the fast component to take place takes between 2 and 4 minutes. Now, if you think back to when we evaluated the ATP-PC system, full resynthesis of phosphocreatine stores takes about 3 minutes, which sits right in between here. So that is my main focus first of all, is to resynthesize these stores of phosphocreatine. That's going to take 2 to 4 minutes. Then, in this time, I'm going to use 3 to 5 litres of excess oxygen. Now I said here, And at the start, prior to exercise, my minute ventilation and my oxygen consumption was 20 litres a minute. So during this period of time, my oxygen consumption is going to be between 23 and 25 litres per minute. Okay, so it remains elevated. So I have an excess amount of oxygen there, right? 3 to 5 litres extra. Now that oxygen, where is it going to? Okay, it's going to replenish my myoglobin. Right, remember, myoglobin extracts the oxygen from the capillaries and it uses it for aerobic respiration. But because I've been using up that oxygen during exercise, the stores will be quite low of oxygen. So I am making sure that through breathing heavier, okay, getting an excess amount of oxygen, that I'm going to replenish those stores of oxygen. So because of this extra oxygen that I have, allows me to resynthesize my phosphocreatine stores through P plus C plus energy. Now, I said before, I've broken this P and this C apart, and now I can't use them as an energy source again until they're put back together. So what I need to do is I can't just they don't just float back together and they're fine. You've got to use energy to bind them back together. Okay? So the P and the C come close together. Energy binds them back together, but energy isn't free. You don't just get given the energy. So this energy here is provided through aerobic respiration. So that aerobic respiration, you need oxygen for it to take place. But I'm needing excess amounts in order to, first of all, make sure that I've got enough for aerobic respiration in general. And the excess oxygen in the aerobic respiration is now sticking back together the P and the C. So that is the fast component of EPOC. So if I just break it down bit by bit, first of all, we know it takes 2 to 4 minutes. Okay, it's also known as the lactic acid component. It's going to use 3 to 5 litres of excess oxygen, and that excess oxygen is being used to replenish the myoglobin stores with oxygen. Now that they're replenished, they can resynthesize stores of phosphocreatine, and they can do this through P plus C plus energy, and that energy is used, or it comes from aerobic respiration. So that would be the fast component of EPOC. Then I also have the slow component, all right, which is known as the lactic acid component, and that is where we usually associate in the past straight away with when we finish exercise, we just remove lactic acid. Our first priority is this for the body, then also I can remove and recycle lactic acid. I want you to think back to when we did energy sources. If you remember, we put lactic acid is an energy source, right? And you're kind of going to see why now, because not only will I remove it, I can also recycle it. So let's have a look at the slow component then. So first of all, you'll notice that I've got massive biceps and Jamie's got tiny biceps. But the main thing is that we've got lactic acid in the muscle. So let's just remind ourselves how lactic acid is bad. The main thing is it denatures enzymes. Okay, remember, I've got enzymes such as creatine kinase, ATPase. So if I can't use those, I can't break down energy sources. So it needs to be removed from the muscle. So and we associate it being removed via oxidation. All you need to think about is that that excess oxygen that I am breathing in during this period of time, the lactic acid will be exposed to oxygen, therefore removes it. Okay, to keep things really, really easy. This is the main thing that you want to happen with your lactic acid. So lactic acid is in the muscle. It can then get shuttled through the blood to the liver. And when it's in the liver, it will take this lactic acid and it will convert it into energy sources. This process is known as the Cori cycle. Now, think about how I got to lactic acid. I must have been using the lactate anaerobic system, which is glycogen gets broken down into glucose, glucose is broken down into pyruvate, and then pyruvate converts into lactic acid. The Cori cycle in the liver just reverses that process. So it would take this lactic acid, convert it into pyruvate, then some of it will get converted back into glucose, and some of it will even get converted back into glycogen. So through this process, my glycogen stores that would have been depleted through exercise can now be resynthesized back without eating any foods. All right? Obviously, you would still eat some foods, but that you can do it naturally through your body. Then, some of it gets converted back into protein. It's going to help to support the process of recovery after exercise. So this isn't so much a process, but it's thing you just need to remember that happens. So some can get removed via oxidation, is exposed to oxygen. Some is sent back to the liver for the Cori cycle to take place, where lactic acid is converted back into pyruvate, glycogen and glucose. Then, some can be excreted via sweat and urine. And you need to remember during all this time, you are going to have an increased oxygen consumption. Now, it's not good. This whole process can be done in about an hour. Okay? It's where you remove your lactic acid. There's sometimes be lactic acid left over, but the main process of it can take about an hour. Now, think about an hour after exercise. You're not sat there panting, right? You're not there breathing really heavily. So in the fast component, we said, well, it definitely uses between 3 and 5 litres of excess oxygen. That 3 and 5 litres, you can really tell that you're taking it in, because your breathing rate would massively increase. Whereas with this, it could be, if we said that our oxygen consumption at rest was like 20 litres a minute, and this is how we're breathing now, it might be like 20.5, okay, or 21. Not so much that you would notice it. Okay, however, you would be taking potentially deeper breaths, and you would potentially have an elevated breathing rate during this time. So, if we take the slow component out of here, we're going to look at it, and it's just about the different things that can happen with a lactic acid. So, it's known as the lactic acid component. Remember, I've got the alactacid component and the lactic acid component. If you can't remember which is which, the lactic acid component is the one that concerns itself with doing stuff with lactic acid. So, some of it will get removed via oxidation, okay? Some of it will be transported back to the liver for the Cori cycle to take place, whereby it can get converted back into pyruvate, glycogen and glucose. Then some of it will get converted into protein, some can be excreted through sweat and urine, and during this time the performer is going to have an increased minute ventilation, also an increased oxygen consumption at this time, because the performer their body is still working harder than normal in order for these processes to take place. Okay, so that's it in terms of the theory of EPOC. Okay, in the next video we're going to look at the actual how it would look in terms of a question.